is our final project presentation for operating system. My team is MCMANNEMENT ESSAU Backhem, ANAK PUTRA GANTI, MIRZA SYAHMINA BINTI MUSTAFAR, NASIRA BINTI NASER, and MOHAMMAD ARMIN bin ERAMLEE. For this project, our main objective is to implement a round-robin CPU scheduling simulation using 100 synthetic processes. We evaluate the scheduler by testing three different size quantum values, which are 3 milliseconds, 10 milliseconds, and 25 milliseconds. During the simulation, we measure key performance metrics such as average waiting time, average turnaround time, and total context switching overhead. Based on this measurement, we identify the optimal time quantum under the given system constraints. For this background CPU scheduling, in a multi-programming operating system, the CPU is shared and limited resource. At any time, multiple processes may be waiting in the ready queue, but only one process can execute on the CPU. Therefore, CPU scheduling is required to decide which process should run next. Effective scheduling helps improve CPU utilization, reduce waiting time, and ensure fairness among processes. Without proper scheduling, system performance can degrade and some processes may experience long delay. Next. For round robin overview. Round robin is primitive CPU scheduling algorithm that is widely used in time sharing system. Each process is assigned a fixed time quantum. A process execute until the quantum expire or it finish execution. If the process does not complete within the allocated time, it is preempt and placed back at the end of the ready queue. This approach ensures fair CPU access for all processes. However, the overall performance of round-robin scheduling strongly depends on the chosen time quantum. Next.
Okay, next I will present about a system design. So first, the system is made up of four main components. They are the process generator, the round robin scheduler, the ready queue, and the timeline manager. The process generator creates 100 synthetic processes with random arrival time and CPU burst duration. The scheduler control how these processes are executed using the round robin algorithm, while the ready queue store the process that are waiting for uh, CPU time. The timeline manager track the global simulation time in milliseconds, including the execution time and context switching overhead. Next, I will explain about process control block. So next, each process is represented using a process control block or PCB. The PCB store important information such as the process ID, arrival time, CPU burst time, remaining execution time, finish time, turnaround time, waiting time, and completion flag. This value allow us to accurately track and evaluate process performance throughout the simulation. Next, I will explain about scheduling, logic, and context switching. The ready queue is implemented using FIFO structure with the C++ STL queue. Instead of storing full PCB object, the queue stores process indices to reduce memory usage. A Boolean vector is also used to prevent duplicate entries in the queue. The round robin scheduler continues a cycle. At each step, newly arrived process are added to the ready queue. If the queue is empty, the simulation jump forward to the next arrival time. Otherwise, a process is given CPU time based on the time content or its remaining time. So lastly, context switching is model fixed 1.0 millisecond penalty applied after each process transition. Finally, the simulation timeline is managed using a global current time variable, ensuring that all performance metrics are calculated accurately and consistently.
Thank you, Mac. So first, I will explain the performance metrics used in this evaluation. Average waiting time or AWT refers to the average amount of time process spend waiting in the ready queue before it gets CPU execution. Average turnaround time, or ATAT, measure the total time taken from when a process arrives until it finishes execution. This includes both waiting time and execution time. Lastly, total CPU overhead represents the cumulative time lost due to context switching. It is calculated by multiplying the total number of context switches by the switching cost, which is this case it is 1.0 millisecond. Next. Next is this table show the result of for three different time quantum values. Q1 equal 3 millisecond, Q2 equal 10 millisecond, and Q3 equals 25 millisecond. For total context switches, Q1 recorded the highest number at 921, while Q2 reduced it to 3 to 7. The lowest number of context switches was achieved by Q3 was with only 157, presenting an 82.9% reduction compared to Q1. Similarly, total CPU overhead follows the same pattern. Q1 has the highest overhead at 9 to 1 millisecond, Q2 is low at 3 to 7 millisecond, and Q3 achieved the lowest overhead at 157 millisecond. In terms of average waiting time, Q1 has the highest value at 2506.90 millisecond. This decreases to 2115.21 millisecond for Q2 and further reduces to 1796.30 millisecond for Q3, giving a 28.3% improvement. For average turnaround time, Q1 again performs the worst at 2532.97 millisecond. Q2 improves to 2143.65 millisecond, while Q3 achieved the best result at 1824.27 millisecond with a 28.0% reduction. Next, based on analysis, a small time quantum result in the worst performance due to excessive context switching and high CPU overhead. Medium time quantum provides more balanced performance with moderate overhead and improved waiting time. However, a large time quantum delivers the best overall performance as it minimizes context switching, reduces CPU overhead, and achieves the lowest average waiting time and turnaround time. Therefore, in this experiment, the large quantum value Q3 is considered the optimal choices. Thank you.
So for this part is the conclusion for optimization. Like Armin said before, so based on our simulation result, the main goal was to determine the optimal time quantum for round-robin scheduling when context switching overhead is considered. We test three different quantum size 3 millisecond, 10 millisecond, and 25 millisecond. The result clearly showed that the smallest quantum, 3 millisecond, performed the worst. It causes excessive context switching with 9 to 1 switch, leading to very high CPU overhead and long waiting time. When we increase the quantum to 10 millisecond, performance improved significantly. Context switch were reduced and both waiting time and turnaround time become better. These show a good balance between fairness and efficiency. However, the best performance was achieved with a 25 millisecond quantum. This configuration produced the lowest number of context switches, the smallest CPU overhead, and the shortest waiting and turnaround time. Therefore, we conclude that for this CPU-bound workload with noticeable context switching cost, a large quantum of 25 milliseconds is the most optimized and efficient choice. Next. So in conclusion, this project successfully demonstrate how time quantum size affect the performance of the round-robin scheduling algorithm. Our findings show that Round-robin efficiency is highly dependent on the balance between quantum size and context switching overhead. While smaller quantum are often preferred for responsiveness, there can significantly degrade performance when the switching cost is high. In our simulation, the 25 millisecond quantum achieved the best overall performance, reducing overhead and improving both waiting and turnaround time. This study highlights an important real-world insight: operating system must carefully tune scheduling parameter based on workload characteristic and system constraint to achieve optimal performance. So that's all from us. Thank you.